Today we're going to look at composition of functions, and this is just basically saying how are we going to take two different functions, put them together to build a new function. So the first way we're going to look at it is just doing some algebra, some basic addition, subtraction, and maybe just some function notation to get used to if we're taking a look at the sum of two functions or the difference. So if we have the f function and we have the g function, two different functions, and we are going to combine them. So the sum of two functions, instead of saying f plus g of x, we could have it written as f of x plus the g of x. Okay, same thing for the difference. So I could see f minus g of x. It's the same thing as saying I'm taking the f function and then I'm going to subtract out the g function. For the product, I could say take the f function and multiply it by the g function. And finally, the quotient division, we're going to say the f function divided by the g function. And now this we have to be careful with. Since we have a fraction, we always want to think, all right, well, can't have 0 in the denominator. So this is based on the fact that g of x cannot equal 0. Okay, so we're going to try some of these. So we have two different functions down here. We have our f function, which is x squared. We have our g function, which is the square root of x plus 1. So we're going to combine these through addition, and then we're going to give the domain of each. Basically, at the end, take a look at the function and tell me what the domain would be. So if I take the f function, x squared, I'm going to add to that the g function, which is the square root of x plus 1. That's my new combined function. Now, if we're going to take a look at the domain of this, we have to think, well, the domain, where are my restrictions? Anything under the square root has to be greater than or equal to 0. So if I solve, I can see, well, x has to be greater than or equal to -1. So the domain for this function includes -1, but -1 being our lowest number, and we'll go all the way out to positive infinity. Okay. Taking a look at letter B, very similar, only difference here is now we're subtracting these two functions. Okay, so nothing really crazy. Now, domain, same thing, nothing has really changed. I still cannot have numbers that are going to be less than -1 out to infinity. Okay, now the product, same idea. So I have x squared this time times the square root of x plus 1. Again, the only issue we have is that value under the square root. So again, our domain not changing, still -1 out to infinity. Division, that's the one we have to be careful with. So writing the function, not too bad, just simply divide them. The only other thing we have to think about now is because not only do we have the square root, but we also have a denominator. Okay, so we know that that value cannot be less than 0. Normally, like in our first three, we said it could equal 0, but because it's in the denominator now, it cannot even equal 0. So the only thing we have here is, well, x plus 1 has to be greater than 0. So when we solve, you're going to see a slight change in the domain and the fact that the domain this time cannot equal -1. So now I'm going to have to show a soft bracket, -1 out to infinity. And then the last one, well, what if I have two of the same function? Well, I just do the same thing, multiply them together. So I could write them separately. I could also say, well, it's going to be the square root of x plus 1 quantity squared. Okay. The domain on this, now I want to think of my original function, g of x. We had always said, well, I cannot have a -1. I'm sorry, I can't have a -1, but I can't have anything less than a -1. It's still going to apply here. If I plug in anything less than a -1 into this x value, I'm going to have a negative number under the square root, and that is not going to be good. So our domain here is still going to be from -1 out to infinity. I know the temptation is to say, well, if I square a square root, it's gone, I don't have to worry about it. I want to think of the actual function itself, which is the square root of x plus 1 when considering the domain. So that's some basics, addition, subtraction. We can also compose functions. So a couple things here with at least notation. We can see it written with this open circle. When I see this open circle, f of g of x, that's the way that we're going to be reading it. Same exact idea process as this other notation where I see parentheses rather than the open circle. Okay. The one thing you want to think to yourself is if you have this open circle notation, you're always working from the rightmost function to the left. It's kind of like a backward process. Just like when we're on the parentheses, I want to think inside to the outside. And I'll show you what I mean by this. Big thing we want to understand, and we're going to take a look at this numerically, is that function composition is not commutative, meaning once you switch the order around, you're going to get some other function. Okay, so we're going to take the two functions, e to the x and the square root of x, and we are going to compose them. So the very first thing we're going to do is find this f of g of x, which keep in mind that's a different way of writing it like this. So this is saying I'm going to take the f function, and anywhere I see an x in my f function, I'm replacing it with g of x. So I'm replacing it with the square root of x. Okay, so I go into my f function, and the f function is e to the x. So anywhere I see an x, I replace it with the g function, the square root of x. And that's our composed function. Okay, now if we read it going in the opposite direction, g of f of x, and keep in mind the notation for that is g parentheses f of x. Okay, so the order now has changed. That is saying I'm going to take the g function, and anywhere I see an x in the g function, I'm going to replace it with the f of x, and the f of x function is e to the x. Okay, so we start with the g function. G function is the square root of x, so I see my x value and I replace that with e to the x. So those are our two composed functions. They look different. And it also says, okay, let's try and verify numerically that that composition is not going to be the same, and proving it's not commutative. So let's just try, for instance, we're going to say let x equal 2. And if we were to plug this in on your calculator and we do e to the square root of 2, all right, we're going to get something that's about approximately 4.113. And if we did the same thing for our g of f of x, we have the square root of e to the 2. And again, that's going to be approximately about 2.718. They're not the same. They are not equal. So that's trying to show you there that the composition is not commutative. You want to be careful with the order that you do things in, otherwise you're going to get different results. Okay, now the very last thing that we're going to talk about is decomposition. So decomposition is going backwards. It's saying I have a function and I want to break it up into two functions. Now again, we want to be careful with the notation. So if I'm looking at this, it says my f function is made up of that composition of f of g of x, meaning I'm taking whatever the g of x function is and plugging it into the f of x. So the nice thing with decompositions is you can always check them, and you can always make sure, recompose them, and make sure you get back, in this case, h of x. What I'm doing here, whenever I think about this, I always try and think, can I find perhaps a parent function, one of our 12 basic functions? If I can, make that f of x. If I can find maybe any repeated pattern or a non-parent function, that would be my g of x. So for instance, for this first example here, I'm not finding like a parent function or a 12 basic function, but I do see something repeated. I see that x plus 1. So what that's telling me is, well, that's probably going to be my g of x. Why? Well, because I'm going to plug that in to my f function anywhere I see an x. Okay, so that's also telling me, well then, that must have been like an x to begin with. Same thing over here, that repeated section, well that must have been an x to begin with, and add 4. So now again, I can try that. I could compose that and actually say, well, what if I were to plug in x plus 1 into x squared and plug in x plus 1 into 3x, and sure enough, I do get h of x back. Okay. If we try example B over here, now same idea. I'm going to think either find a parent function for f of x or find something repeated for g of x. Well, I don't see anything repeated, but from a parent function, one of my 12 basic functions, I see it kind of looks like we have a square root of x. Okay, so what does that mean? Well, anything that's not part of that 12 basic function, which is all of that x cubed plus 1, that looks like that's going to be my g of x. That's saying anywhere I see an x in my original f function, I can plug that in. So if I were to plug that all in, 2x, I see I can compose h of x back. Now sometimes when you do these decompositions, there's more than one way to do this. They do take a little bit of practice to kind of recognize the functions at hand. So again, let's try this. F of x, make it a parent function. G of x is, if there's anything repeated, typically that's your g of x. Nothing repeated, so I'm thinking parent function, 12 basic function. I could write this as perhaps 1 over x. So what does that show me? That shows me my denominator, x squared plus 4, must be the g of x function, the stuff I'm going to plug into f of x to make h of x. And again, is there more than one way to do it? Sure. I just found this one. This worked for me. If I recompose it, I will get h of x. Okay. And our last example here again, f of x, if I can make it a parent function, one of my 12 basic functions, or g of x if it's anything repeated. So again, I'm not seeing repeated, but I do see a 12 basic function, e to the x. So that means, okay, what must I have plugged into f of x to create h of x? I must have plugged in x plus 4. And so decomposition, it does take a little bit of time, it takes a little bit of practice. The more you do it, the easier you're going to see these patterns. Okay, hope you like this. Like and subscribe. Have a great day.